Alright, physicists, welcome to our February 3 edition of Physics. Today we are getting ready for our test on Friday. And you notice that I have my gladiator quote. I used to use this as a gag when I was a high school teacher, and last night I found out that I've been doing the quote wrong. I used to think that it was the emperor who said it to the gladiators, who said, "To you who are about to die, I salute you." And I always used to use that as a gag when I was a high school teacher before tests. But now I find out that it's the gladiators who say it to the emperor, and the gag doesn't make sense anymore. So this might have to be my retirement of that bit. Okay, so here's what we'll be looking at today. I last time showed you the formula sheet that you'll get for the test. And so today we're going to try to go over a whole bunch of problems which are on a review sheet that I hope that you complete before the test. So I want you to try it out. I've given you the answers to the questions. I want to go through in this video all of those questions and try to get you started so that you'll be able to get the right answers on them. And so I hope through this video, no new stuff in here, you can appreciate that we actually have covered some ground and we've made a little bit of progress, and you can feel a little bit good about having learned at least a little bit of physics since you came here at the beginning of the year. Okay, so let's begin. All right, so our first chapter of our book was unit conversions, problems with train tracks. I don't have a ton of stuff on the test on this, maybe about 2 questions, but since there are there, let's make sure we know how to do them. This is a good sample type of question because it makes you use your SI units off of the table on the equation sheet. Let's see how you would do that. You want to do grams in terms of atomic mass units. So 1 gram, and all you get to do is multiply by 1. Okay, so let's see. I have how many AMUs are in a kilogram. So I could go ahead, kilogram. Kilo is 10 to the 3. So 10 to the 3 grams is 1 kilogram. And then I need to go from kilograms to AMUs, so 1.66 times 10 to the minus 27 kilograms. 1 U equals, and then the grams cancel out, kilograms cancel out, 1 times 1 times 1 on the top, divided by 10 to the third on the bottom, divided by 1.66 times 10 to the minus 27th on the bottom. Okay, very good. Now, the thing to be careful about in this type of a problem is make sure that you don't make just a calculator error. Sometimes what I see people do is do something like 1 times 1 divided by 10 to the third, divided by 1.66 times 10 to the minus 27th. And then you get an answer that's really small instead of the right answer, which should be really big. So make sure that when you're dividing by stuff, you have correct parentheses around that whole thing in the divisor, so that you don't end up with something very wrong. I did not point out last time, but I did give you on your equation sheet a little bit of extra help for a couple of geometry facts. So radius of the circumference of a circle, area of a circle, surface area of a sphere, volume of a sphere, some stuff about cylinders and triangles and stuff like that. So I will give you a problem involving this. In this type of problem, though, it says a sphere with a radius of 1.7 centimeters has a surface area of, well, sphere of radius r, the area is 4 pi r squared. So that's the surface area. is going to be 4 times pi times 1.7 centimeters squared. And as before, I would need to use a couple train tracks to do my unit conversion. And 1 centimeter, or let me do it with this. Centimeter is, centi is 10 to the minus 2. So 1 meter is 10 to the minus 2 centimeters. And then remember, our trick is that if you have 2 copies of centimeter on the top, this is centimeters times centimeters, you have to have 2 centimeters on the bottom. So 1 meter squared goes with 10 to the minus 2 centimeters squared. So this would be 4 times pi times 1.7 times 1.7 divided by 0.01 divided by 0.01. Okay? All right. So that's enough unit conversions. Now let's take a look at some of our ideas defining motion. So we've talked about speed, how many meters you're going per second, velocity, which is speed with a direction attached to it, acceleration, which is how your speed is changing in time, and then we talked about a little bit about how you can use derivatives to go from position to velocity to acceleration. Keep taking time derivatives. And if you want to find basically your displacement in velocity, you take the integral of the acceleration. And if you want to find your displacement in position, you take the time integral of velocity. Okay, so here's a sort of easy problem, hopefully. It says a car starts from hither, goes 50 kilometers in a straight line to yon. Hither and yon. 50 kilometers. Immediately turns around and returns to hither. The time for this trip is 2 hours. So you go there and you come back. And that time is 2 hours. The total distance for that is going to be 50 miles there, plus 50 miles back would be 100 kilometers. So the speed that he's going, the average speed is going to be 100 kilometers over 2 hours equals 50 kilometers per hour. Okay, that's one of my options. Is that the right answer? No. The thing to realize is that they have asked you for the average velocity. Average velocity. Average velocity is total displacement over total time. What's the total displacement if you start out at hither and end up at hither? The total displacement then is 0 kilometers, and that means your average velocity is 0 kilometers per hour. Now that seems funny, but keep in mind velocity has a direction. Positive velocity means you're going forward. Negative velocity means you're going backward. And if you have the average of those, a positive and a negative, you're getting that overall 0. Okay, here's a different sort of problem. A car travels 40 kilometers. At an average speed of 80 kilometers per hour. And then slows down and travels another 40 kilometers at 40 kilometers per hour. Okay, the average speed of the car for this 80 kilometer trip is, Okay, well, you know the total distance, which is just going to be 40 kilometers plus 40 kilometers equals 80 kilometers. How would you find the time? Well, T1 would be the distance divided by the speed, so 40 divided by 80. And then T2 would be the 40 divided by 40. And then your total time over that whole range would be T1 plus T2. And then you could find your average speed by taking your distance, your total distance they traveled divided by your total time. So I'll let you try that. By the way, I should say I have given you the answers to these in your review, so don't feel like I'm being stingy here. I want you to go and do these problems on your own as review for the test. Okay, so you know how to find average speed is total distance over total time. You know how to find average velocity, that's total displacement over total time, where you end up minus where you started out over time. Then we have instantaneous velocity. Well, instantaneous velocity you're going to get from the time derivative of the position with respect to time. What does that actually mean? It means slope. So here we have a graph of x versus t. What's the story here? Our person goes forward 12 feet quickly, stands around for 3 seconds, and then comes backwards a little more slowly to her original position. Okay, now here's 7 seconds. What is the instantaneous velocity at t equals 7 seconds? Well, v has to be let's take 2 points where we can really tell it. Final position, 0, minus initial position, 12, over final time, minus initial time. Okay, now you might be saying to me, Cordall, that looks to me like the average velocity. You're right, it is the average velocity, but if you are not accelerating, your average velocity and your instantaneous velocity can be the same. Okay, so good enough. All right, so another skill that hopefully we've picked up over the last couple weeks is reading position versus time graph and being able to tell a story about it. What kind of story do we have for each one of these graphs? Here you've got a position versus time. Person's going forward, getting faster. Person's going backwards at a steady rate. Person's going backwards but slowing down as they go. Person's going forward and slowing down as they go. And here we have a person going forward at a nice and steady rate. Okay, so which one of the five coordinate versus time graphs represents the motion of an object whose speed is increasing? That would be this one. Okay, as I said, it is good to be able to read graphs. Let's do the same thing with this. You got a position versus time. What sort of story does each one of these graphs tell? This one is going forward at a steady rate. What is this one? This one is going forward. How do I know it's going forward? It's because the v is positive. It doesn't have anything to do with the slope of v. It has to do that with its a positive value. And the acceleration is positive, so in this case, it's going forward and getting faster. Here's the acceleration versus time. Acceleration is positive, and the acceleration is in fact increasing, but that doesn't necessarily tell me whether I'm going forward or backward. If I'm going forward, I would be getting faster. If I were going backwards, I would be getting slower, faster. All right. What does this one say? It's a flat graph. Sometimes when people see this, they want to say, oh, flat graph means not moving. But notice it is a velocity versus time graph, so this actually means just moving forward at a steady rate. And this again is an acceleration versus time graph, so you can't say exactly what it means, but if we're going forward, it means that you're getting faster because the acceleration is in the direction of movement. If you're going backwards, this would be getting slower because the acceleration would be opposite the direction of movement. Okay, so from that I think you can figure this out. Which one of the 5 graphs represents motion at a constant speed? That would be this guy and that guy. Okay, so enough with just definitions. Let's actually do something with this and start to use our accelerated motion model. Now, I just want to emphasize, this test is an hour-long test. So if there's any question that seems to be taking a long time, you're probably doing it wrong. So one of the things that I want you to take away from the next couple minutes of this is a lot of success on the test just has to do with looking at what you have and using it. Don't reinvent the wheel every time. You can always use the tools at hand to get the job done. Okay, so let's tell a story and then try to pick out an equation that's going to give us the answer we need. All right? So here's the story. We've got a racing car traveling with a constant acceleration, increases its speed from 10 meters per second to 30 meters per second. Okay, so it's speeding up over a distance of 60 meters. Okay, so it's going more slowly here, and it's going more quickly over here. How long does this take? Okay, so let's identify what we have and what we want. We have, I guess, x naught equals 0, x equals 60. We have v naught equals 10 meters per second. And v equals 30 meters per second. It asks, how long does this take? If I'm asking how long, that is asking a question about time. What don't I have? I do not have A. Okay, so what I would do now is look at my constant acceleration model equations. Now, as I've said before, these two at the top are really all of the model. But if you are short on time, it might be worth looking at one of these solutions where it's already sort of been solved for you and use one of those. So in this case, we don't have A. Let's look at for one of these equations that doesn't have A in it. That has A. This doesn't have A. That has A. Okay? So I would use this equation and solve for T. Okay, let me say that again. We listed out what we had, then we looked for an equation that had the requirements, that it didn't have the variable that we didn't want, it did have the variable that we do want, and then we used the equation to solve. Okay, so not rocket science, it's racing science. All right, now, as we said in the last part, but we didn't really do anything with it, you can use derivatives to go from position versus time to velocity versus time to acceleration versus time. And I would not be afraid of that type of problem if I were you, because it's kind of a gift. It's just a standard, easy procedure that I think everyone in this class is pretty competent at. So let's, for instance, look at this case. It says, over a short interval near time equals 0, the coordinate of an automobile in meters is given by x equals 27t minus 4t cubed, where t is in seconds. Okay, so that 27 has to be in units of meters per second, and then this 4 has to be in units of meters over seconds cubed to cancel it out. All right, it says at the end of 1 second, the acceleration of the auto is, well, if I am writing this out, I should say, oh, no sweat. I will just take my derivative, 27 minus 3 times 4 is 12, t squared, and then take the derivative one more time. Derivative of a constant is 0. 2 times 12 is minus 24 t, and then I put in 1 second in for t, and I'm done. All right, very nice. Is that the hardest problem you can think of with this sort of thing? Unfortunately, it is not. Let's take a look at a little bit more of a tricky problem with this. Okay, it says, the coordinate of an object is given as a function of time by something. Okay, let me write it down. X equals 4t squared minus 3t cubed. So this is actually 4 meters over seconds squared, and this is actually 3 meters over seconds cubed to cancel out the cubed. Where x is in meters and t is in seconds. Its average acceleration over the integral from t equals 0 to t equals 2 is, and I think, oh, great, acceleration, I know how to do this. And I start taking derivatives. 8t minus 9, 3 times 3 is 9t squared. And then it hits me. Oh my goodness. Average acceleration. What? How am I going to find average acceleration? And then it hits me. Oh yes. Average acceleration is just the change in velocity over the change in time. So, if I can find at t equals 0 what the velocity is, and I can find at t equals, so all I did, I put in 0 there, I put in 0 there, got 0. And I can put in at t equals 2 seconds what the velocity is. Okay, so then it's going to be 8 times 2 minus 9 times 2 squared. So that's 16 minus, okay, 9 times 4, I guess that's 36. 16 minus 36 is minus 20 meters per second. Okay, then I can find out what the average acceleration is. A average equals final v minus 20 meters per second minus initial v minus 0 meters per second over time. 2 seconds minus 0 seconds. All right, and so there I get my minus 10 meters per second squared. All right, so that's, notice that it's different from the instantaneous acceleration. It's something different, and you need to know how to be able to solve for either. All right, now everything I've said about solving for position or displacement or average velocity or average acceleration or instantaneous velocity or instantaneous acceleration, it all can be translated from 1 dimension into 3 dimensions. How? Using vectors. Okay, so this I think was on your homework homework 3, this is where I saw the most problems because people are a little hesitant to draw a picture. They want to just use their math. But there's a lot of cases where drawing a picture will help. Some of these, though, you also need to just know how to crank through the math. So we'll do some examples of each here. Okay, notice I have not given you the pi radians equals 180 degrees. I expect you to know that. Of course, this is the picture that you want to have in mind is that if you have a wedge who has a length of r and r and r, that is what an angle of 1 radian means. And so 2 pi goes around the circle, so if you have going around the circle, that's 1, 2, 3, 4, 5, 6, and some change. And so that's what a radian means. Okay, now let's think about vectors. Now, if you want to find the vector magnitudes, it's just using the Pythagorean theorem every time. How does that manifest in, for instance, in 3 dimensions? This is an example where you have an x, y, whoops. I don't think that's here's the traditional way to draw it. X, y, and z. So we're going 2 out in the x direction, 6 out in the y direction, and then -3 in the z direction. So there's our vector pointing down there. Okay, and we want to find out how long is that arrow. Well, the way that you find it is just by taking, in this case, the size of that arrow is going to be the square root of 2 squared plus 6 squared plus -3 squared, and you square it, it becomes a positive number, and there you go. It should be one of these. Okay, so finding the vector magnitude is easy, and it just involves Pythagorean theorem. Vector components is also sort of easy, but usually it will require a little bit of thinking and drawing a picture maybe. So let's do that in this case. Never eat sour watermelon. Okay, from your window you can see a high-rise several blocks away. You check a map and see that the building is 560 meters away from you in a straight line in a direction 30 degrees south of east. Okay, 30 degrees south of east, and so that's 30 degrees, and this is 560 meters. So the idea is that you have to walk along the cross streets. You can't just walk through the buildings that are between hither and yon. And then how would you find the sides of this? Well, that side of your triangle would be 560 times cosine of 30. Usually, if you set up your coordinates in a nice way, you're using cosines for x. And in fact, if you wanted to think about this as a 0 to 360 type of situation, I might even put a -30 there, where because it's 30 below, and then this would be 560 times sine of -30, and then you get a distance in x. This would be your x component, this would be your y component. And notice for this one, you would get a negative number because you're going south rather than north. For this one, you would be getting a positive number because you're still going east rather than west. Okay. Now, let's say you want to add two vectors together. What does adding two vectors mean? Well, if you look at this picture, if you have a vector A, that's our blue vector, and B, that's the green vector, adding two vectors together means that you're taking one vector and then taking the next one, and you're moving it over parallel and putting it, the tail of it, on the tip of the last one. And then the final A plus V vector is from the tail of the original vector pointing to the tip of the final one. Okay? Now, that geometric idea is sometimes a little bit hard to figure out how you're going to do it mathematically. So the trick is you split up each vector into XYZ components, and then you add them up. So, for instance, here, A plus B, we give you some new vector, which is 6 meters times I, 6 plus 2, plus 8 meters times J, and then minus 3 plus 1 would give you minus 2 meters times K. All right, so that's the whole thing. The thing to be careful about is that I would definitely be okay giving you something like find S equals 3A minus B, or something like that. And in that case, you'd have to take 3 times each one of these components, so 6 meters times I, plus 18 meters times J, minus 9 meters times K. And then minusing off a vector would mean subtracting each one of the components. Okay? So you can come up with more exotic. And of course, there's a geometrical interpretation of that as well, but I don't have a nice picture for it on this slide. All right, so here's an example with vector differences. An object moves from some position xyz to a different position xyz in a time of 5.3 seconds. What's its average velocity? Okay, now, we said that the instantaneous velocity was delta x over delta t. If we're going to do this as a vector, we have to have our x at the end minus our x at the beginning over our t at the end minus our t at the beginning. Okay, so I'm going to write out each one of those positions as a vector, and it'll make this easy. So x2, that's our final position, is 3.3, comma, minus 1.1, comma, 4.2 meters. So that's the x component, y component, z component. x1 is, they give me x component minus 2.1. They give me a y component 3.7. They give me a z component 1.4 meters. Okay. Now, if I want to take the difference between the two, I take the difference between each of the components. So 3.3 minus 2.1, so let's call this vector our delta x. That'll be 3 minus 0.1 is 0.2, 3 minus 2 is 1. Okay, here's our final minus our initial, minus 1.1 minus 3.7. Whoops, I did the first one wrong. If I minus a minus, it's a plus. My fault. I apologize. So this should be 3.3 minus a minus 2.1. So that's 0.4. 5.4. Count myself. Okay, this is minus 1.1 minus 3.7. So that's minus 4.8. And then for my last one, I have minus 4.2 minus 1.4. Yeah. Just checking to make sure I have these right. Minus 2.1, 3.7, 1.4. Yep. 3.3 minus 1.1. This should be plus 4.2. There's the issue. Okay. So this one's going to be plus 4.2 minus 1.4. And there we go ahead and 0.8. 2.8. Okay, so the idea is okay. And then to find the average velocity, you're going to go ahead and then divide each one of those by 5.3 seconds. So 5.4 divided by 5.3, 4.8 divided by 4.3, blah, 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 blah. Okay? So that's the basic idea. Okay, now getting to the end of things, two-dimensional motion. So we did problems with accelerated motion in one dimension. Now we're going to try a couple of problems with accelerated motion in two dimensions. All right, let's see how it works. Now, as I told you last time, I am going to give you equations for projectiles, but these are really only useful in very specific cases where you're shooting a ball from the ground, it goes up, it comes back down, it hits the ground. So in that case, I give you an equation for R that just depends on V naught and the angle that it's shot at. So that could be useful for that specific instance, but not really otherwise. These formulas for circular motion, however, if there's anything involving circular motion, you're definitely going to use at least one of them, probably both. Okay, so I promise, this is my cross my heart, hope to die promise, I will give you a short answer question on this classic physics problem. We have a bomber flying in level flight with constant velocity drops a bomb before it is over the target. Yes, that's good. Well, I mean, it's bad if you're against war, but it's good if you're trying to achieve your goals as a bomber. Why? Well, as you see, the projectile goes in a curved path, and its speed is increasing in the y direction, but not in the x direction. In the x direction, the velocity vector is remaining constant. Okay, so which one of these is not true? The bomber is over the target when the bomb strikes. That is true. Notice why is that? It's because the x direction velocity is not changing. The acceleration of the bomb is constant. Also true. What is it? Negative 9.8 meters per second squared in the y direction, in the up and down direction. See, the horizontal velocity of the plane equals the vertical velocity of the bomb when it hits the target. That doesn't have to be true. This speed and that speed are probably not going to be the same. The bomb travels in a curved path. Yes. The time of flight of the bomb is independent of the horizontal speed of the plane. Also true. Why is it true? Well, it's true because the initial velocity in the y direction is 0 unless you shoot the bomb downward. So in that case, the time, the only thing that determines how long it takes to hit the ground is the initial elevation of the plane. Okay, let's give you an example problem, something for you to do tonight when you're studying. That's pretty similar to this plane bombing problem that I put on the test. Okay, a stone is thrown outward from the top of a 59.4 meter high cliff with an upward, oh, I take it back. This is not very similar. It's good to know how to do it though. 59.4 meter clip with an upward velocity component of 19.5 meters per second. How long is the stone in the air? So that's the type of path it's taking. It's not. It doesn't really have any lateral dimensions. So this is still just a one-dimensional accelerated motion problem, despite the appearance of being a two-dimensional one. How long is the stone in the air? Assume that it lands on the ground below the cliff and that the ground below the cliff is flat. Okay, so let's see. What would we use? Let's just look at our standard plane equation. Now, let's write down some things. This is where we start out, so that would be our y naught. This would be our y at the end of the story. This would be our t equals 0. This would be our t at the end of the story. And we know what our initial velocity is. Okay, so we know our initial position is going to be 59.4 meters. We know that our initial velocity is going to be 19.5 meters per second. We know that our acceleration is going to be minus 9.8 meters per second squared. How did I know that? That's my gravitational acceleration regardless of mass. Gravitational acceleration does not depend on the mass. So what would I do? Well, I could stick in all of my information into this equation. X at the end is 0 minus x at the beginning would be that 59.4 meters. 59.4 meters equals v naught 19.5 times t plus 1/2 times minus 9.8 meters per second squared times t squared. So that's an equation that does tell me how long it takes to hit the ground. Now, to solve this analytically, you'd have to use your, minus b plus the square root of b squared minus 4ac all over 2a. You'd have to get this into your quadratic formula form and blah, blah, blah. However, you might say to yourself, hey, Cordall, we never used the quadratic formula in this class. That is not fair. And I would sort of agree with you. But notice in this problem, you have these options for times. So you could try them out in this equation and see if one of them basically works, and that would be your right answer. So you could do it without knowing your quadratic formula. And I would say, hey, buddy, that's an okay question. Next. All right. Uniform circular motion, a particle moves at a constant speed in a circular path. The instantaneous velocity and the instantaneous acceleration vectors are. Okay, notice in uniform circular motion, your movement is always going tangent to the circle, and your acceleration is always going towards the center of the circle. So those two are always perpendicular to each other. The rest of those are wrong. Here's another type of problem that I love to give on this type of issue. If you have two objects traveling around different circular orbits with a constant speed, they both have the same acceleration, but object A is traveling twice as fast as object B. All right. Acceleration of A equals acceleration of B. So this acceleration we're talking about, the v squared over r, centripetal acceleration. But object A is traveling twice as fast as object B. So VA equals 2 times VB. the orbit radius for object A is what times the orbit radius for object B. Okay, so if I write in this, I know the accelerations are the same, so that means VA squared over RA equals VB squared over RB. This shouldn't have a square on it. Then I can stick in the information that I know. 2VB for VA. 2VB equals VB over RA over RB. Now, if you're clever, you can at this point see that if you put this has 4VB squared on the top, you would need a factor of 4RB to make those the same, so it's 4 times as big. But if you're not that clever, you can go ahead and multiply this out. Then this would be 2 squared, and then solve your equations for 4RB equals RA. And there you go. So I will give you a problem like that. It won't be this problem, but it will be similar to that, where you change a different variable. Okay, so we're at the end of our hour. Let's take a look at a challenge problem. This is a good one because it kind of puts together some of the things that we've done in this unit. The idea is that you have a Ferris wheel going around, and when you're at the top of that, you're at a height of r plus r, of 2r. The Ferris wheel with a radius of 8 meters makes 1 revolution every 10 seconds. Okay, so then you can find out that the speed that this person is going around is 2 pi times r over t. Okay, so 2 pi times 8 meters divided by 10 seconds will give you the speed with which that object's going, that person is going. When he is at the top, essentially a diameter from the ground, he releases a ball. We've introduced a character now. Okay, so he releases a ball, he has some speed, and that ball now is going to go ahead and make a trajectory until it hits the ground. Okay, so how far from the point of the ground directly under the release point, I'm asking from here to there, does the ball land? Well, the way to do this problem is that you first have to find out how long it takes to hit the ground, and then you find out how far it would, because the speed, this v, in the x direction does not change. So the fact that it's being released right at the top tells you that all of the velocity is in the x direction, not in the y direction. So from the y direction, you can use your accelerated motion equation to set up your, well, let's just use this directly. It would be final position of the ball would be 0 minus initial position of the ball would be 2r equals v dot for that would be 0 minus 1/2 g, let's have g as a positive number there, t squared. Okay, so this would give you a way to find t, and then in your x direction, you could then just find your big R, your range, would just be your v times t. That's just a constant velocity. So and then you'd use the T that you find in there. So that one's a little challenging, but and I don't think I'm going to give you anything that hard on the test, just because it requires some scaffolding. If I give you something like that, I'll have it as a multi-part short answer question. So let's just review the structure of the test quickly. 10 multiple choice questions, essentially like the ones that I've shown you here today. 5 true or false questions, and then 5 multi-part short answer questions. Notice that we have 20 points plus 5 points plus 30 points. That's 55 points. And the thing is going to be scored out of 50 points. So you could get 110% on this test. Wow, that would be cool. But yeah, we're just putting in a little wiggle room. It's the first test after all. Okay, so what are the short answer questions going to be on? Well, the first one's going to be definitions of motions with differences and derivatives. So things about, so I'm going to give you a position versus time equation that has t's, t squares, t cubes maybe in there. You're going to find things like average velocity, instantaneous velocity, average acceleration, instantaneous acceleration, things like that. Then I have a problem where you roll a ball up a ramp. I give you the speed of the ball partway up the ramp, the how far the ball, how much time it takes the ball to get to the top. I have you find the acceleration. I have you find out how far the ball rolled up the ramp. Okay, stone on a rope. I have you calculate the centripetal acceleration. I have you calculate the period. I have you tell me what direction the centripetal acceleration is. It's always towards the center of the circle. Playing with a bomb problem, you find out how long it takes to hit the ground. You find out how far the bomb travels after it's released. Okay, so that's essentially the problem we showed you. And then finally, the cannonball at an angle problem is the one where you shoot a cannonball. You've got to get the x and y components of the velocity, and then I ask you to calculate, how high up the cannonball is after a second or something like that. Okay, so that's what you should expect for the test. I don't want you to be surprised. I definitely would encourage you to review your homework, review the homework solutions, review the packet that I gave you today that has all these questions on it. All right, so good luck studying. If you have any questions, make sure to email me.